stuff. We were the talk was held by Finlay, but he gladly freed his spot to David, and he will tell us about the stochastic optimization for energy systems. Yeah. So the stage is yours, and I think someone was the presenter.
Will you take a clicker?
It's behind here.
Oh, okay.
Okay.
Yeah, okay, so good morning. My name is David, and I'm a research assistant at NTNU. I'm working together with Finlay. We saw his presentation on Wednesday. And today I want to tell you a little bit about a paper that we have been working on in the last months and that we are hopefully going to publish soon, I guess next month, but still not sure. And yeah, so in our department, the main research we are doing is about energy systems. So all the presentation will be about the optimization of a unit commitment problem. And specifically, we will focus on stochastic optimization. So first of all, to tell you what is optimization under uncertainty, it's a kind of optimization that involves variables which are random, which we will refer to as chi. So whenever you see a chi in the whole presentation, means that this variable is a random variable. There are three different approaches that one can use to solve these kind of problems. One of them is what we call recourse modeling. In this approach, we split the optimization problem into different stages, and at every stage, two things happen. First, we optimize a certain set of the decision variables, which we call here y, and then the random variable collapses into one of the possible values it can get, and then we do a second stage decision of a second set of decision variables, which we call x. The second approach that one can use for optimization under uncertainty is Ribez modeling. And in this case, it's I'm no expert on it, but it's I think it's a bit simpler because you just assume that the random variable will take the worst possible value, so the most restricting case. And in that way, you make sure that whenever you optimize in the future and the outcome of the random variable is any other outcome, whatever you will get will be better than what you got before. And the specific case that we focus in this presentation is chance constraints, which is quite interesting because it's a problem where we have, as we know, a minimization of a certain objective function that depends on the decision variables, and it can also depend on the random variable. But what we impose is that the probability that a certain equation is met has to be larger or equal than p, which is what we call the reliability level. So now that we already know how the chance constraints are defined, I can go a bit more into what the unit commitment problem is. So some of you might already know it, but essentially, it's a combinatorial optimization problem that aims to minimize the cost of scheduling several electrical generators while they meet some constraints. Some of these constraints can be, for example, meeting the demand at every time period, or also some technical constraints that the physics behind the generators impose. So the way how I told you now what the unit commitment problem is, this is a simple way, which is a deterministic unit commitment problem where we know everything, we know all the parameters. And what we want to do is to assume that the demand, instead of being a deterministic case, is instead of being a determined value, it's a random value. We will consider that the demand follows a normal distribution over all the time period, so overall is a multivariate normal distribution. And the way how the chance constraints would look is what you can see here. It's the probability that the total power produced by the generators is larger or equal than the demand at every time period. That this whole thing, the chance that this happens is greater or equal than P. So the way how this is defined here with this equation is something that you cannot really solve with a quantum annealer nor with a classical solver, because you have an equation with a probability. What should you do with this? So you need to do something here. You need to reformulate this into a kind of problem that you can embed either in a quantum annealer or in a classical solver. So that's what we do. What we will do is to convert this problem into first into a mixed integral linear program, and I will explain afterwards how we do this. But the reason for that is because then when we have an MILP, we can actually go to D-Wave and solve it with a hybrid solver. And then from the MILP, we can go into a QUBO by doing some changes that I will also explain. And then once we have a QUBO, as we know, we can go to the pure quantum linear from D-Wave. At least that's the theory. We will, spoiler alert, it might not be possible, but that's the goal. So the way how you do this reformulation into an MILP is, as we said, the demand is follows a normal distribution, specifically a multivariate normal distribution. And what we will do is to gather an n number of samples that follow this distribution. And we will impose that a percentage of these samples is met. To do that, what we do is we introduce a new variable, which we'll call y. And this variable is a binary variable. When the y is equal to 0, as you can see on the top of the slide, we impose that the power is greater than 0, which is not a constraint, no? Because if the power is greater than 0, that's just the native constraint of the variables. But when y is equal to 1, we impose that the power is greater than the demand, which is actually what we want. We impose that the demand is met in this specific scenario, because y has a subscript I, and this I is associated with each of the scenarios. So the first constraint we impose is that for every scenario, we have to meet this power greater or equal than d times y. And then we have a last constraint, which is imposing that we have to have a certain amount of y's, which are equal to 1, that fulfills this reliability level that we set before in the first slides, this p. So that's why p times n will be the amount of samples that we want to be met. So from this, it's clear that the larger n is, the more accurate the problem will be, no? But also the more complex, because we have more variables, we have more constraints, and then the whole thing is more complex. So we have to find out what is the appropriate n to have a nice result or a good result, but also that is not too complex. So we can go into the results of what we get once we solve this with the hybrid solver from D-Wave. First, I recommend you to ignore the green plot, and I will explain it a bit afterwards. But if you check on the red one and the blue one, the red one corresponds to a classical solver, to Gurobi, while the blue one is the results from D-Wave, from the CQM solver. And what we observe is that for instances so n was this number of scenarios that we get from the normal distribution. When n is smaller or equal than 15,000, which is medium small complexity, we observe that Gurobi is actually able to outperform D-Wave, which is expected. But the nice thing here is that when we go to large complexities, the CQM is able to find lower energy solutions. And yeah, I have to remark here, I didn't say it, that all these runs have been done with the same time limit, both for Gurobi and D-Wave. This time limit, if I'm not wrong, is something like 25 seconds or 30 seconds. So when you set the same time limit and you increase the complexity a lot, you observe that D-Wave is actually able to outperform Gurobi. We also have to keep in mind that we don't take into account here the embedding time, which probably if we check on the clock time, it would not look like this. So it's good if you have a single embedding for many problems and you can reuse it, then this is an actual outperformance of D-Wave. Yeah, so what we can grasp from this part of the plot is that the hybrid solvers may be a bit more effective in large scales settings and they run under tight runtime costs. So for the second part of the plot, which is what I told you earlier to ignore, which is the green one, the second part, the green plot is what we call the BLP. So this was an experiment that we wanted to check, which is to convert this MILP problem into a fully binary program, but still keeping the constraints. So it's not a QUBO, because we have the constraints set as constraints, but we change the continuous variables, we approximate them by being integer, and then we use a binary encoding to put them in the problem. And what we observe is that there are many points that are missing here, and they are not really, the solver cannot really find feasible solutions. And that tells us that somehow the solver is struggling a lot to find a solution in a problem that there's some kind of binary encoding. We could say this is due to the amount of variables, but it's actually not the case because the amount of variables that you have on the last very point of the green plot is much less than the amount of variables that you have on the very right of the blue plot, which means that the reason why this is happening is not because there are too many variables. So our guess, and this is just a guess, we cannot really say that because of what we have already discussed several times in the last days, is this thing about the black box from D-Wave. We don't know what's going on there, but we see that the binary encoding is causing problems. And this could mean that they are kind of doing some simulated annealing. The reason for that is because, as you might know, simulated annealing is a process where you do single bit flips of a certain state, and depending on if the energy of the new state is lower or higher, the probability that you change to this new state is higher or lower. So what happens with the binary encoding is that, imagine, for example, that the optimal solution requires that one of the integer variables is 8. 8 in binary would be 1, 0, 0, 0. And imagine now that the current state where you are is 7, which in binary is 0, 1, 1, 1. To change from 7 to 8, you need to do 4-bit flips. But this process is just doing 1-bit flip. So this makes it easy to get stuck in a local minima. And if these minima are infeasible, then we get stuck there. So that could be the reason. It's something that we cannot say for sure because we don't have access to what's going on there, but this is a guess. So after checking on the hybrid solver, we want to try to check on the pure quantum annealer. And as we said, to go to the pure quantum annealer, we have to convert the problem into QUBO. And let's see what happens if we set the number of scenarios that we checked. So earlier in the previous slides, we said n was the number of samples that we get from the multivariate distribution. Let's set n to 10. N is a very low number. So ideally, you need thousands. But we set it to 10, and we observed that the number of variables is 800, and the couplings is 26,000, which is insanely large for what the state-of-the-art quantum annealers can do nowadays. This is a nice graph of the QUBO problem. I put the slack variables corresponding to the demand around because otherwise it was a mess, as you couldn't really see the shape of it. But you really see that it's very dense. There are many variables, many couplings, and this is too large for a quantum annealer. That's why we decide to, since we want to check how the quantum annealer behaves, we decide to go to a deterministic case. It's not the main goal of all this, but at least to have a good taste or a hint of how the annealer works, it might be good. So here you can see the graph of the QUBO of the unit commitment. This is a unit commitment with 3 time periods, 3 generators, so quite small. But still, the number of variables is large. It's around 300, so 291, and 5,000 couplings. And this is something that technically it could be embeddable in a pure quantum annealer. But we know that the topology of the annealer, so your result will depend a lot on the embedding, and the embedding depends on the topology. And the topology, we know it's quite homogeneous, and this is not really a homogeneous graph. There are lots of clusters there. So that's why when we tried with a pure quantum annealer, the solutions were not really neither feasible nor nice or like optimal. So that's why we decided to go for simulated annealing. But we have to remark that whatever we are doing here with simulated annealing will be possible to be used in the future when the wave has more connected topologies. So when we go to simulated annealing, as we said before, we need a QUBO, no? Because still we are trying to solve a QUBO. And as we already know, QUBO has this big issue of the Lagrange multipliers. What do you set there? As you said before, Alexei, it's something that you have to make a decision here what to do. So what the approach that we decide to take here is to design a simple algorithm that allows to optimize them. And the algorithm works as follows. So first you have a QUBO where you set the Lagrange multipliers on 1, so the smallest value they can get. We fit the annealer with this QUBO, and then we check on the feasibility of the solutions. And we compute what we call the feasibility ratio, Ri, for each of the constraints, which is the ratio of the constraints that meet this constraint, so the amount of solutions that meet the constraint over the total amount of solutions. This means that when Ri is a large number, means that this Lagrange multiplier doesn't need to be increased more because all the solutions are feasible. When R is small, you need a big increase here. And the way how we apply this is we consider a sigmoid function that like activates this more or less depending on how far you are from what you want. So once we reach either a certain number of iterations or all the feasibility ratios reach a threshold that we decide, then we leave the algorithm and we save all the lambda values. So we do this and we get some lambda values that you can see on the right. What you can see on the left is the plot corresponding to the evolution of the feasibility ratios at every iteration. You observe, so ideally they would always increase, not every iteration, because that's why you do this, to increase these feasibility ratios. But you have to keep in mind that the more you increase a multiplier, the less feasible other constraints are. No? So in the end, it's about trying to find the sweet spot between all the constraints such that we have as many solutions which are feasible as possible. And on the top left, you can see the constraints mostly involving the binary variables of the problem. And on the lower left, you can see those that involve not the continuous, but like the binary encoded variables. On the right is the important feasibility ratio, I would say, which is what we call the joint feasibility ratio, which is tells us the amount of solutions that are completely feasible, that meet all the constraints. And we see that by the end of the algorithm, which is at 50 iterations, the percentage of solutions that is feasible is 4%. And yeah, we obtain these values for the Lagrange multipliers. And once we have them, then we can do a final run, trying to find more solutions and see the feasibility histogram of these solutions. So that's what we have here. With the multipliers that we had before, we run these on the simulated annealer, and we get, I think it's 10,000 solutions. And among those 10,000, we see that 11% of them are feasible, which is fairly good, because it could be that actually it was difficult to reach this 11%. But what we observe is that the best solution of those feasible ones has a relative error of 8%, which is, it's quite good. Like for being the situation where we are, which is simulated annealing with a binary encoding, with a Lagrange multiplier tuning that it's not perfect, but it's something that gives us a good idea of the values of these multipliers. It's quite of a good solution. But if you check on the average of all the feasible solutions, the error is 30%, which is quite large. And ideally, we would like to reduce this a bit more. So as a conclusion of all this, we can say that, first of all, the pure quantum annealers are not really competitive because the state-of-the-art classical solvers are very powerful. And yeah, I think we need to invest a bit more time on developing more highly connected annealers and less noisy, and in general, because this is always for small problems, for toy problems, but what you want to solve with this is an actual industry problem, which is far in time, but it's in the future will come. Another thing is that yeah, the hybrid solvers show promise when we scale them to large complexities and when the time limit is very, very short and very tight compared to classical solvers such as Gurobi. And the final thing is, yeah, that as we have been discussing, that the obscurity of this hybrid solver makes it a bit difficult to analyze what's going on inside and to analyze the performance of it. So that's all from my side. If you have any questions, I'm happy to answer them.
Thank you very much, David, for the talk.
Thank you.
And just some of our insights. So are there questions?
Yeah.
Alexei.
Do I understand correctly that you pre-generate scenarios for the random variables. You had this capital N, and you said, okay, this many standards, you generate them yourself, right?
Yes, so I like you get a whatever function that gives you points in a multivariate normal distribution, and I decide to get, I don't know, 1,000 points, 1 million points, whatever. And then we store them, and we consider as many of them as we want to in the optimization problem.
Yeah. My question would be, of course, do you consider, or do you think it's possible to use quantum parallel to do just that, to have like different scenarios, like for example, you had a demand in a quantum register, and you created a different position of different scenarios. And
Yeah.
then you somehow solve like your decision variable would be what the word not entangled to the demand variable.
Yeah.
I expect it to be equivalent to Monte Carlo, but
Yeah, this is quite of a Monte Carlo. It's similar because in the end you consider like random samples. But yeah, this idea of considering, like we have in our department also, I think you, Pascal, have heard about it. It's the idea of considering the stochasticity of the qubits and so on for the scenario sampling is something that it's in the back of our heads. It sounds promising, but it's something that there's not much about it, so we have to investigate from the ground because it seems like it's reasonable, no? I mean, if you have random variables and you know the stochasticity of quantum physics, like it seems like something that could match, but we have not done it here. I think this is something that probably would fit more with something related with gate-based quantum computing. Because with quantum annealing, sometimes it's something that you can really tune